Howdy, and welcome to this lecture on products of vectors. Okay, so we know that vectors are important pieces of information or important quantities that we use in physics and mathematics, and that vectors are generally described as something that carries more than one piece of information, as opposed to, say, a scalar, which is a quantity that provides one piece of information. And we also know that vectors, because of that nature of having two pieces of information embedded within the information of a vector, that we can't do simple, ordinary arithmetic addition when we add two vectors. So, for example, if we have vector A, and say this is defined as having a length of 5 units at an angle that's, say, 30 degrees oriented up from the horizontal axis, and then we define vector B to be a length of 6 units having an angle of 36 degrees oriented up from the horizontal axis. If we want to add these two vectors to see what the resulting vector is, we know that it's not equal to 11 with, some combination of the theta, right? We don't even know what we would do with the theta since those two angles are different, right? And the way that we have to add these two vectors is to orient their projection on the xy plane and know how they sum with each other relative to that xy plane. Or another way to say that is that we can determine the components of vector A and the components of vector B and add the respective components together to then get the final resultant components of vector C, and then describe it in terms of magnitude and direction, if that's how we wanted to present that information. So we know that when we do manipulation of vectors, we have to be careful in terms of what we ordinarily think in terms of things like addition and subtraction. And the truth is that's also going to be true when we multiply vectors, okay, or what we call vector multiplication. So there's essentially two types of vector products. The first type of vector product is the projection of one vector parallel to a second vector and when we do that, it results in a scalar product. And so as a result of the fact that this operation results in a scalar product, we call this the scalar product of two vectors. And as we'll also learn, we call it the dot product. The second vector multiplication is when we project one vector perpendicular to a second vector. And we'll talk about what this means when we say parallel versus perpendicular. And when we project one vector perpendicular to a second vector, it results in a vector product as opposed to a scalar product. And so we call this the vector product of two vectors. And we refer to this one as the cross product. Okay, so let's talk about each of these separately. And the first one that we'll talk about is the scalar product. Okay, so the scalar product is the one where we project one vector parallel to a second vector. Okay, so let's suppose we have a young boy, young man, Jack, pulling on a string connected to a box being dragged across the floor. Okay, so here's a little picture of what we have. So we have the floor, we have this box, and there's a string attached to it. And then we have Jack, and he's holding on to the other end of the string with his hand, and he's pulling it, okay? And Jack is walking in this direction. So as Jack is walking in this direction with a string in his hand connected to the box that he's dragging across the floor, we can see that the box is also going to be moving in the same direction with some velocity v, and it's moving because Jack is applying a force that is parallel to the taut string that's connected to the box, right? The string that's in tension connected to the box. And let's suppose that Jack walks a certain distance or a certain displacement, and that displacement will be the vector s. And of course, force is a vector as well. So what we will realize is that there's an interaction between the vector force and the vector s, okay? So, first of all, let's just remember that force is a vector, and displacement is a vector. So we have two vectors interacting with each other, and the vectors, or the interaction, results in an effect. Okay? So the question then, what is the effect? It might be tempting at first to think that the effect is that the box is moving. But we have to pay very close attention to what we're saying here. We're saying that force and displacement are interacting with each other, and that interaction between force and displacement is creating an effect, okay? So yes, the Jack pulling on the box with the string, applying that force, is causing the displacement, but there's an interaction between force and the resulting vector s, the displacement, that creates an additional effect, okay? And so the effect that we're referring to is actually something that we can't see, okay? And so the effect between the interaction of the vector f and the vector displacement s is a quantity which we call work. Okay? And work We'll talk more about work as time goes on, but work is a type of energy transfer. Okay, and like the discussion of work, which will occur later on, we'll also talk about energy transfer later on. Okay, and so Jack pulls on the string F. That causes the box to move, a displacement S, but we also realize that there's this interaction between the vector F and the vector displacement that results in a third parameter, a third quantity, which we call work or work transfer. Okay, so how do we quantify that interaction, right? So how do we quantify between the vector F and the vector displacement? That is, how do we quantify work transfer? Okay, well, let's take a look at our vectors on the typical xy plane. And essentially what we have is we have something like this where we have a vector S, which we're just going to, for simplicity, draw parallel to the x-axis. And then we have this other vector F. And what we'll notice is that when the component of F, right, remember that F has two components, S ordinarily does as well, but because we've drawn it parallel to the x-axis, it only has an x component. But force clearly has two components. There's a y component, F of y, and there's an x component, F of x. Okay? And if we just kind of think about this conceptually for a moment, it's F of x that is causing the box to move in the direction of S. It's not F of y. F of y is perpendicular to the direction of S. And so that box is sliding across the floor, a displacement S, as a result of F of x. And it's that component of F of x acting in the direction of S that results in there being an energy transfer. In other words, F of x causes the box to move a displacement S, which is to say it caused motion. F of x is actually what resulted in motion of the box. And because there was motion of the box, there was an energy transfer associated with that motion, and we call that energy transfer work transfer. So let me write down in words what I just said. It's F of x that causes the motion of the box to displace S F of x causes motion, and there is energy transfer associated with motion. We call this energy transfer associated with motion work transfer. Thus, it's F of x that results in work transfer, not f of y. Okay, so then we say, okay, well, how do we quantify this work transfer? Okay, well, again, if we just think about this conceptually, we know that f of x is what's causing the motion, and we know that f of x causes motion a displacement s. So we can quantify the energy transfer or the work transfer associated with that motion to be the magnitude of f of x times the magnitude of the displacement s. And because f of x is applied, or because the magnitude of f is to be applied in the direction of s, we correspondingly call that, or multiply that by cosine of theta. Okay, so if we define theta here, right, the cosine of theta is going to give us the component f of x. And so we can define this work transfer, which we'll use the letter W to indicate the work transfer, is equal to the magnitude of our force F times the magnitude of our displacement S times the angle between the force F and the displacement S. Okay? And again, what this quantity, the reason why we come up with this quantity is we have the force acting on the box causing the displacement S, but it's only the f of x component that's causing that displacement S, and so we have correspondingly the cosine of theta present in our equation. So you notice right away, of course, that work, notice that I don't have the vector quantity or the vector symbol above work, okay? So work transfer, so note that work transfer, W, is a scalar quantity. It has no direction associated with it. It's just an amount. It's just a quantity of something. And it's a quantity of how much energy was transferred to the box to slide it across the floor, a displacement S. And you could say that it was the energy that Jack put into the box to move it, a displacement S. Okay? But it doesn't have direction, right? Energy doesn't have direction associated with it. And so this work transfer is a scalar quantity. It is not a vector quantity, okay? Okay, so the way that we can now recognize what we've done here is we've taken the projection of F in the direction of S, and that's what gave us our scalar product, okay? So what we did is we took the projection of F in the direction of S to determine the work transfer. Okay? Okay, so because when we do this, right, when we do this multiplication, this vector multiplication, because we result in a scalar product, we of course call this operation the scalar product of two vectors. Okay, so because the result of vector F projected in the direction of vector s results in a scalar we call this operation the scalar product. And the way that we very often write this is we'll have vector f, and then we'll use the big dot, a bold dot. I'll talk about that in just a moment. And then the vector s, resulting in the scalar w. And so because we use the dot, and by the way, the dot is borrowed from our typical use of multiplication, right? Remember that, we'll sometimes algebraically write 2.3 is equal to 6, okay? Notice that there's a little dot here, right? But we use a big bold dot here, more or less just to remind ourselves that this is a multiplication of two vectors as opposed to a multiplication of two scalars like what we have in the case of 2.3 is equal to 6, okay? But because we use the dot to symbolize the scalar product of two vectors, we'll also often refer to this as the dot product. Okay, so because we use the dot to indicate the scalar product of two vectors, we often call this operation the dot product. Okay? Okay, so what's interesting now is if we look at, so in our example that we showed here, when Jack was pulling on the string, the force was obviously some angle theta relative to the vector s, okay? So we can have theta vary anywhere within this coordinate plane. There's two particular cases where it's very interesting to understand exactly what's going on, right? The first is when f is parallel to the displacement. Okay, so again, if we have our y and our x-axes, and let's suppose that this is our scalar s, and then let's also suppose that f is parallel to s, okay? So in the case of f being parallel to s, the vector f is fully projected onto s. It's in the exact same direction. It's parallel to it. So the resulting scalar which is, of course, the magnitude of f times the magnitude of s times cosine theta. And of course, in this case, theta is equal to 0. So then cosine theta is equal to 1. And we get that the scalar product is equal to simply the magnitude of f times the magnitude of displacement s. And that's for theta equal to 1. And so basically, all of the componentry of force goes into the displacement s, resulting in the corresponding work transfer. Likewise, we can have the other extreme, which is when force is perpendicular to s. And so again, we can have our vector s, and then we can have our vector force. And of course, now theta is equal to 90 degrees. And so force is completely perpendicular to S. There is no component of F that can be projected onto S. So in the case of being perpendicular to S, no component of F can be projected in the direction of S so the resulting scalar work transfer is equal to the magnitude of F times the magnitude of displacement times the cosine of theta. And now we have theta is equal to pi over 2, which means that cosine of theta is equal to 0. And so the work transfer in this case is equal to 0. Okay? So again, if we go back to our example with Jack pulling the string, if he were to be pulling his string at some angle, theta, less than 90 degrees relative to the horizontal, the box would drag across the floor. But then if he decided to move his string so that it was straight up and down and apply the same force, assuming that he didn't apply such a strong force that the box lifted off the ground, the box would obviously not move, right? He would just simply be holding the string in tension with some level of force F, okay? Okay, in which case there would be no energy transfer, there'd be no work transfer, because there would no longer be any motion, right? There was no motion associated with the application of that force. Now, real quick, and again, we're going to talk about energy transfer and work transfer more later on, but it's a good opportunity at this point to remind ourselves that just because a force is being applied to something doesn't mean that there's an energy transfer taking place, okay? A good example is, for example, the forces that hold up the legs of your chair, right? As you sit on the chair, you are applying a force to that the legs of the chair, and that force is being transmitted through the legs of the chair to the floor. And of course, the floor is providing a reaction force that is at least as much as the force of your body sitting on the chair, right? And so that balance of forces results in there being no motion, there's no displacement, and therefore there's no energy transfer, right? With you sitting on a chair that's not moving, there's no energy transfer, right? So there's no work transfer taking place there. So there's a difference between force and energy transfer. Force results in energy transfer when that force causes a displacement, okay, as we can see in our work equation. Okay, so we've talked about how we basically have defined the work transfer as the vector force dotted with the vector S. That's another way that we would say this, right? The dot product of vector force F with vector displacement S results in the scalar quantity work transfer, okay? Now, we can write this in more general terms with just any two arbitrary vectors, and we can say the following. So thus, in general, we define the dot product, also known as the scalar product, of any two vectors vector A and vector B as So vector A dotted with vector B is equal to the magnitude of A times the magnitude of B times the cosine of theta between the two vectors, and that is equal to the scalar quantity C. Okay, so just as a reminder, A is a vector, B is a vector, magnitude of A is, of course, the square of the components, the square root of the square of the components, right? Ax squared plus ay squared plus az squared, square root that whole sum. Same thing with that magnitude of B. Cosine of theta is the angle between A and B. And then, of course, C is a scalar. Okay? No direction associated with it. And so we can write this in our vector components very easily. And so we can say that A dotted with B is equal to the component of AX times the component of BX plus the component of AY with the component of BY plus the component of AZ with the component of BZ. And of course, that's all equal to C. Okay? Also, what's kind of interesting, because you result in a scalar and there's no direction associated with it, the dot product does have a commutative property of the vectors. And so you can, A dotted with B is basically the same as B dotted with A. They're commutative, which of course equals the scalar quantity C. Okay, so that's what happens when we determine the projection of one vector parallel to the direction of a second vector, okay? And so then the question becomes, what happens if we were to look at the application of a vector perpendicular to a second vector, okay? And real quick, just to be clear, this is not the same as what happened here, right? Where we said, okay, well, if force is applied perpendicular to S, then the result is 0, right? But we have to be very careful with our language here, because remember that what we're doing when we look at this force that's perpendicular to S, when we're calculating the dot product, what we're doing is we're calculating the component of F that is perpendicular, or that is parallel to the vector S, right? So if the force F is perpendicular to S, then there's necessarily no component of F that is parallel to S. So the dot product, in other words, that part of F that is parallel to S is necessarily equal to 0, okay, by definition. But that doesn't mean that if F is applied to a vector, or if one vector is applied perpendicular to another vector, that there isn't some kind of a result, okay? And so our second operation, multiplication operation of vectors that we're going to talk about, is what we call the vector product. And just as we said before, the vector product is when we project one vector perpendicular to a second vector, and this actually results in a third vector. Okay, so the vector product, and we call this the vector product as opposed to the scalar product. So the vector product results in a third vector, which is what we call the vector product itself. Okay, so what does it mean? First of all, what does it mean to say that we are applying one vector perpendicular to another vector? Okay, well, probably the easiest way to think about this is to consider a hand wheel, okay? And so in this hand wheel, so this could be like a steering wheel, for example, right? And so what we have on this steering wheel is actually 3 planes of motion, okay? And so what are these 3 planes of motion? Well, the first is the what we would call the, oh, this isn't going to let me draw in here, I don't think. Okay, maybe if I click on it, I can draw on it here. Okay, so the first plane, or the first axis, excuse me, is this direction that we have from, say, the center to the top of the wheel. And then another axis is from the center of the wheel to the other edge of the wheel. And then the third axis is that axis that runs along the stem of our hub here, okay? And so it's a bit difficult to see, and I'm going to try drawing it another way. But ultimately what's going to happen is we're going to define this distance from the center of the wheel to the edge of the wheel. We're going to define that as r, or the moment arm, okay? And that's a vector because it has a magnitude and a direction. Likewise, we're going to define a force which is applied to the edge of the wheel, okay? And you can see, of course, that that force application is perpendicular to the moment arm r. Then that's going to cause this wheel, so if this wheel, say this wheel were fixed in the center here, right? This were, say, connected to your steering shaft in an automobile. By applying the force across the moment arm, that's going to cause this wheel to turn a direction, okay? And what we're going to learn is that the application of this force across the moment arm r induces a torque in this wheel, which causes that wheel to turn, okay? And so this center hub that we have is going to move in a rotational direction, and the direction of that rotation is going to be along this axis that runs through the center of the hub, which is orthogonal to both R and F. And so there's necessarily three axes of motion here. There's the easy axes to see, which would be, say, F in the Y direction and R in the X direction. But then this rotational motion along this third axis is along what we call the Z-axis, okay? So let me try to draw this in another fashion. Okay, and so we have, for example, our axis in the Z direction, right? And so this would be the center axle that the wheel is going to connect to. And then we have in our other two axes the steering wheel, okay? And so there's a moment arm that's applied here, and then there's a force that's being applied in, say, the X direction. So now R is in the Y direction and force is in the X direction. And then going into the paper would be our Z-axis, which is causing there to be a rotation along that Z-axis in the direction of the axis of the Z-axis, okay, the direction of the Z-axis. Okay, so that's essentially what we mean when we say that we have two vectors that are perpendicular to each other, resulting in a third vector, okay? And so when we apply this force across a moment arm R, it results in a third vector, which we call torque, okay? So torque is the result of a force acting through a moment arm R that causes motion in the axis perpendicular to both the force F and the moment arm R. Okay? And so at this point, it can be a little bit confusing as to how this torque is actually resulting in motion in the third axis. And so this is when using the screw as an example or a way to conceptualize this can be very helpful, right? So imagine that you have a screw, okay? So I'm going to try to draw this, and I'm going to draw this where we have Z, that is the horizontal axis, so this is going to be Z. And then we have our two orthogonal axes, and say this is axis X, and then axis Y. Okay, and then we have our screw. So let's suppose that this is, I'm going to draw it a little bit offset here. So let's suppose that this is the screw head. And then, of course, the screw has a taper to it as it comes together in a point. And then there's threads on that screw that cause it to thread into something as it's being turned, okay? So we have now a screwdriver that slots into that screw head, and then there's a handle on that screwdriver, and there's a moment arm between the center of the handle to the edge of the handle, and then there's a force that's being applied, and that force is going, say, into the paper, okay, perpendicular to both X and Z, but parallel to X, okay? So the force is going in the direction of X, okay? And so as that force is being applied, this, and if the force is going into the paper, then that means that the axis of rotation is going to cause this to spin counterclockwise. So in this direction, say that fashion. And what the screw will do is the screw will start to back out. It'll go in this direction, right? And so I have a vector applied in the x direction, F, across a vector in the y direction, R, causing a displacement in the z direction, which is the motion of the screw moving in this direction along the z-axis. Okay? And now if I were to have instead the force F come out of the plane, and so if I were to have the force instead come out, so it's now the force is coming out of the paper, now I'm causing my screw to rotate in this direction, and then my screw is now screwing into the material, and so I move in this direction along the z-axis. Okay? And so this combination of the vector force times the vector r results in this third vector, which we call torque. Okay? So torque, this third vector, is the multiplication of vector force with vector r, the moment arm. Okay? And now you'll notice that because we take two vectors force and radius r, and we result in a third vector, this operation is called the vector product, okay, as opposed to the scalar product, which is how we refer to the dot product, okay? So since the multiplication of force vector with moment arm vector results in a third vector, which we call the torque vector, this operation is called the vector product, as opposed to the scalar product, which we talked about before with the dot product, okay? Now, also notice when I wrote this above, right, torque is equal to force crossed with r, I used x to indicate the multiplication as opposed to the dot symbol from before, right? And of course, we've done that in algebra as well, where we say that 2 times 3 is equal to 6, right? So we use x to indicate the multiplication. And so in this case, when we're talking about vector multiplication, we use the letter x when we are projecting one vector perpendicular to the other vector, right? Notice that force is perpendicular to r. We're applying force perpendicular to r, and that's what's causing the torque, okay? So we use the letter x to indicate the vector product operation of two vectors. And because, of course, the x looks like a cross, we call this the cross product, okay? So we use the letter x to indicate the vector product operation so we will often refer to this operation as the cross product. Okay? Okay, so how exactly do we determine the values of the torque, right? So we would determine the magnitude of torque. So the magnitude of torque is the magnitude of force times the magnitude of the moment arm times the sine of theta between those two quantities, okay? And why is it the sine of theta? Well, if we take a look at what's happening, right, and suppose we draw this a little bit more easily now, and suppose that, for example, we have a door that is connected to a hinge, and I apply a force on this door at the edge, right? And so this then, the length of my door then also becomes my vector moment arm r. Well, as I apply this force, right, that's going to cause the door to move in a counterclockwise fashion, okay? Okay, so again, how does this answer the question of why is it sine theta? Well, what would happen if instead of applying the force exactly perpendicular to the door, what if instead I applied the force in this fashion? Okay. Well, remember that what I'm interested in knowing is the projection of the force F perpendicular to the vector R. Okay? And so I have my right angle, and then I have my theta that is defined here, right? And so it's the side opposite the angle theta, the projection of F onto R, the perpendicular projection of F onto R. It's this quantity here that I'm interested in knowing, okay? And so my magnitude of the torque, the resulting torque, right? So my torque is over here, resulting in that rotation of the door across the hinge. Then consequently, my determining the magnitude of the torque will be the magnitude of my vector F times the magnitude of my vector R times the sine of theta, the side that's opposite the hypotenuse, the sine of my value theta, okay? Okay, so that gives me the magnitude of torque, but remember that torque is a vector, so there's also direction, okay? So then the question is what about direction? And in this case, the direction is one of two possibilities. It's either out of the paper or into the paper, okay? And so, and another way that we can oftentimes indicate direction is the motion is either counterclockwise or counterclockwise, or clockwise, okay? And so in this case here, the torque would be in a counterclockwise motion, okay? So it's counterclockwise or out of the paper. And then the other possible direction would be clockwise, which would be into the paper. The z-axis, the direction of that torque would be into the paper. Okay, and so again, if you're wondering, well, how is this term out of paper or into the paper, where's that coming from? Well, again, imagine that this torque is driving a screw either into the paper or out of the paper, right? And so a screw, we use what is called the right-hand convention for screws, right? And so if I torque a screwdriver clockwise, that causes the screw to go into the paper, right? In other words, the right-hand orientation of a screw is that it drive itself into the material that the screw is going into. If instead I apply the torque counterclockwise to the screw, it's going to cause the screw to come out of the paper, right, or out of the material, okay? And so that's where this counterclockwise would cause the screw to come out of the material or out of the paper, whereas clockwise would cause the screw to go into the material or into the paper, okay? Okay, so finally, we can write a general expression for the cross product, okay? So, of course, for this example, we've been describing this in terms of force and moment arm and torque because this is a very common example of where you have one vector acting perpendicular to another vector that results in a third vector, right? Just like with the dot product, we recognized that the projection of one vector parallel to a second vector resulted in a third quantity, which if we say that the one vector is force and the second vector is displacement, that third quantity is a scalar, which is what we define as work transfer. Okay, so we did the same thing when we were talking about the cross product, where we said that the cross product of force with moment arm results in a third vector, which we call torque. But we can generally write that the vector A crossed with vector B results in a third vector, which we call vector C, okay? And again, while vector A dotted with vector B is the same as vector B dotted with vector A, which is just the scalar quantity C, vector A crossed with vector B is not the same does not equal vector B crossed with vector A. Okay. In fact, it would be the negative. Okay, so if we flip, vector product is not a commutative operation. Okay, vector product does not have the commutative property. And so what we can say, though, is that vector A crossed with vector B is equal to the negative of vector B crossed with vector A. And those, of course, would result in the same result, which would be vector C. Okay. Now, the thing with cross product, and this is even partially true with dot product. So if you remember when we talked about dot product, we said that A dotted with B is just AX times BX plus AY plus BY plus AZ times BZ, and that gives us C. Okay. One of the important things to note about vectors, sort of a foolproof way of not messing up vectors, okay, especially when we start talking about direction and if something is out of the paper or into the paper or what have you, is to always think of vectors and manipulate them in terms of their components. Okay, that's why unit vector and the components of vectors is so important. Okay, so to make cross products foolproof, it's best to do the manipulations with the vector's components. So we can write that vector C, which is equal to vector A crossed with vector B, is given as the component of C in the x direction is the component of A in the y direction times the component of B in the z direction minus the component of A in the z direction times the component of B in the y direction. Likewise, the component of C in the y direction is the component of A in the z direction times the component of B in the x direction minus the component of A in the x direction times the component of B in the z direction. And then finally, the component of C in the z direction is equal to the component of A in the x direction times the component of B in the y direction minus the component of A in the y direction times the component of B in the x direction. Okay? And by doing your cross products between two vectors in the component fashion will make it much easier for you to keep track of your directions and magnitudes and such, and make it a much more straightforward operation for you. Okay, now we talked about dot product in the context of work transfer, right? So work transfer is in fact defined as the dot product between force acting through a displacement. And we talked about cross product in the context of torque, where torque is in fact defined as the force vector crossed with the moment arm vector, okay? But both dot product and cross product have a lot of different elements in physics, okay? Particularly as related to electromagnetism. And so we will largely talk about it in the context of work transfer with the dot product and torque with the cross product. But in your study of physics, it's going to come up in other elements as well. And so it's an important set of tools to be familiar with. Okay? Thanks very much for listening, and I hope you have a great day.